Hopefully you went and tried this problem using Newton's method to approximate the intersection of these two functions and using a starting value of 1. We want to be accurate to within 3 decimal places, so that means basically I can round to 4 when I'm doing all of my calculations. Once again, if you haven't done this yet, please do this, push pause on the video, try it out, and I will start the solution now. X squared minus 1 is equal to sine x. I'm going to create a function. I'll call it h because g and f were already used. It doesn't matter whether you do sine x minus x squared minus 1 or x squared minus 1 minus sine x. Both of these will have roots which cross where the functions intersect. We want to start with an initial guess of 1, I believe. So we're going to start with an initial guess of 1. Let's take the derivative before I get too far into this. H prime would be 2x plus 0 minus cosine of x. So 2x minus cosine x. And we're going to see what happens here. So we start with an initial value of 1. Let's plug that into our function. That gives a negative 0.8414. Actually, 8415 when I round. If I plug that into the derivative, I end up with a 1.4597. So at 1, we're pretty close to 0, but not exactly at 0. So I'm going to take and do Newton's method, apply and get 1 minus the fraction whose numerator is negative 0.8415 and whose denominator is 1.4597. So 1 minus that, I ended up with a 1.5765, rounding to 4 decimal places. We plug that number in to our function and then plug that into the derivative. When I plugged it into the function, I got a 0.4854. When I plugged it into the derivative, I got a 3.1587. We got closer to the root. We didn't hit it yet, but we're getting closer. So let's do another iteration. So we increase the values here. I should say we not increase the values, but we go on and move to the next step. So we increase the step 1.5765 minus the fraction where I take the output of the function divided by the output of the derivative. We end up with 1.4228, rounded to 4 decimal places. When we plug that number into our function, we end up with a 0.0353. When I plug that number into the derivative, I end up with a 2.6981. Again, I'm trying to mix up the notation here. I'm plugging in the number 1.5765 instead of saying 1.7565, instead of calling that x1. You could have also, instead of calling this x2, you could have plugged in 1.4228. We see we're getting closer to 0 here, but we're not there yet. So let's do another iteration. I'm gonna just keep doing the same process. Although I keep writing f in my function, although my function is called h. I don't know. Probably shouldn't have done that. My function is called h instead of f. But that's just a little notational thing. Notice that that's not the biggest deal. So doing another iteration. Gives us 1.4228. That's where our starting point is. And then we're going to adjust that by the fraction whose numerator is 0.0353 and whose denominator is 2.6981. The number I get out is 1.4097. If I plug that number into my function, I ended up with a scientific notation answer. If I put that back into regular notation, you get about 0.000202. If I plug that number, the 1.4097, into the derivative, I get out a 2.6590 when I round to 4 decimal places. If I round to 4 decimal places up there, I'd get 0.0002. You can imagine what's going to happen on the 4th iteration. Our better approximation is not going to change much. We're going to start at 1.4097, and then we're going to adjust that by 0.0002 divided by 2.6590. And when you adjust something by 0.0002 divided by 2.6590, it doesn't adjust by much. I'm typing that in. I ended up rounding, getting 1.4096. And so you can kind of see that rounded to 3 decimal places, the answer is going to be x is equal to 1.4, I guess 10 if I round it to 3 decimal places. That 9 rounds up to a 10. So 1.410 if I round to 3 decimal places. Now, what I was saying earlier, remember these two, solving this equation meant that we were finding the intersection of 2 functions, one of which was the x squared minus 1 function, and the other was the sine of x. So these are going to intersect when x is approximately 1.410. And the intersection point of the 2 functions, it's going to have an x value of 1.410 And the y value is what we're going to get when you plug it in into the original function. So if I take 1.410 and plug it into my function f of x, I get about 0.9881. And if I plug in into g of x, 1.410, I get about 0.987. So if I rounded to 2 decimal places, it'd be about 0.99. If I rounded to 3, it'd be 0.988 or 0.987, depending on which function I plug into. So let's round it to 2 just so that it doesn't matter which function we plug it into. So the point of intersection is that, comma that. Now again, this is one point of intersection. You could reference the graph to see if that's the only point of intersection. This is the point of intersection when you plugged in a 1, but there could be other points of intersection as well. This is how to use Newton's method to find intersection points. Obviously, we've found roots of functions, we've found how to solve equations, and all of this using Newton's method. One last thing I wanted to state before we get done with section 4.1 is that in Newton's method, you can see that this is an iterative process. So this is something you could quite easily program into a calculator with or program into a computer with some basic programming skills, whether you're using a for loop or some other type of programming skills, and it'd be a fairly easy thing to do, 6 or 7 different iterations using some programming or just using some Excel functions, quite honestly. So it's not a hard thing to do using Excel or using computer programming to get a lot of iterations. And if you can do a lot of iterations, you can get really, really, really close to the actual root.